So this is our last chapter, chapter 8, volume of solids. So what this chapter is mostly, up until we get to 8.3.1, is taking a graph and rotating it around an axis, and that creates a solid figure. So let's say we're taking f of x, which is the curve you see here, and from A to B, wherever those are, if we were to take the whole area under the curve, take that whole area, and rotate it around the x-axis, what kind of shape would be created? So when you're creating these shapes, what's normally helpful when you're drawing your pictures is to think about the symmetry of the graph. So I'm not always the greatest at these, but something like that. Wait. So kind of like that, maybe. So I'm kind of recreating f of x. I'm reflecting f of x into the x-axis. And then I have that same area down here. You know what? I'm off by a whole unit. That's why it looks so weird. There we go. So I have that whole area. And then think about how that area was created. So if you take a slice of this area and you rotate that slice all the way around the x-axis, what kind of shape does that slice create? And what it creates is something called a disc. And it is a filled in disc. It is not an empty disc. It's a filled in, very thin cylinder. So that is what we call a representative rectangle with a representative disc. So like here's the representative rectangle, it's just a very thin rectangle. And if you think about rotating that rectangle around, it's going to create your disc. And it's a solid disc. So when you're rotating every other rectangle around, because this area is made up of an infinite number of infinitely thin rectangles. If you take another one of these rectangles and you rotate that around, it creates another disc. So we have, when we rotate this infinite number of rectangles around the x-axis, we end up with an infinite number of infinitely thin discs. So that's why we call this the disc method. And this is one of those things that I struggle with because I'm not great at creating three-dimensional figures, so you do have to use your imagination a little bit. So like what this figure ends up looking like is something like this. Again, doesn't need to be perfect, it's just a visual. So that's kind of what this figure looks like if I were to take it off the graph. So it's like a vase kind of on its side, but it is filled in. So again, remember that this is a solid figure. This is not empty with just the shell on the outside. This is completely filled in, completely solid on the inside. Okay, so when we're thinking about adding up an infinite number of these discs, the first thing we want to think about is, well, what's the volume of just one disc? The volume of a disc is going to be, again, it's a very, very thin cylinder. So that's pi r squared h, the volume of a cylinder. And you should notice that the radius of the cylinder goes up to the function itself. So that's my radius right there, that little blue piece there. So the radius is the function. And then the thickness of the disc is the height of the disc. So how thick the disc is, that's the height of the disc, right? So the height is the thickness of the disc. And remember that we are adding up an infinite number of these discs that are infinitely thin. We want to have disc next to disc next to disc and just have a bunch of them. And all of these discs are going to be different sizes. So for example, like here on the outside, my disc would be larger than my disc right here, which is going to be a little bit smaller than that green one on the outside. So the discs are different sizes. They are not the same disc, but because they are all infinitely thin, their thickness is all the same. So the radiuses will be different, but the thickness will all be the same. So I'm going to put here infinitely thin. Infinitely thin. And when we're talking about infinitely thin thickness, that's going to go to dx. So remember that when we added up area under the curve, that was adding up an infinite number of infinitely thin discs, or I'm sorry, rectangles, and those rectangles had a thickness of dx. So this is basically the same thing, it's just we're adding up an infinite number of discs, and the thickness is still going to be dx. Okay, the thickness of that disc is going to be infinitely small, because we're adding up an infinite number of them. So what this turns into is the volume of the solid, the whole thing, is going to be adding up an infinite number of these discs. So just recall in calculus, how do we add up an infinite number of things that are infinitely thin? We use an integral. So it's going to be the integral from whatever my bounds are, from a to b, of pi r squared h. The h is the thickness, and that's a dx. And then the radius, again, that radius was wherever your disk is, your radius is touching the top of the function from the x-axis. So the radius is just f of x. So whatever your f of x is, whatever that original function was to begin with, that's what you're going to square. Multiply it by pi and multiply it by dx, which represents the thickness. So again, that's the radius, and that's the thickness of the disk. So your f of y, so let's say we wanted to rotate around the y-axis. So instead of rotating around the x-axis vertically, we're going to rotate this horizontally. So we're going to rotate in this direction. So again, I'm going to do my best to make it symmetric. That's pretty good. And this time, because I'm rotating around the y-axis, okay, going from, let's say, this is our A and this is our B. If I rotate that around the y-axis, my disk is going to go in the y direction as well. So from the center to the outside, that's my radius. And then I'm going to try to create the thickness here. That's kind of the thickness of that disk. And instead of the disks all being stacked next to each other, in this case, the disks would all be stacked on top of one another. And I'm going to do my best to draw what this would look like. Something like that. Oops. Something like that. So this is going to kind of look like a funnel. Again, my proportions are totally off. It's fine. It's just a general idea of what this would look like. But keep in mind that this figure here is completely filled in. It is not empty at all. This is a completely filled in three-dimensional figure. So very similarly, we have the volume of a disk, which is pi r squared h. Now the radius going from the center, so going from the y-axis to the outside, that distance is f of y. And that's different than f of x because f of y means you need to have your function in terms of y. Now, why do I need my functions in terms of y? Why can't my function be in terms of x? Like, why can't I just use a regular f of x? Well, if you look at the thickness of the disk, so remember when you're stacking all these disks on top of each other, sorry, I can't draw straight right now. Your thickness is now in the y direction. Your thickness will be dependent on y2 minus y1 because your thickness is vertical. So that thickness is going to be dy in this case. Because your thickness is going to go to dy, that means your function also needs to be in terms of y. So if you are rotating around the y-axis for the disk method, everything needs to be in terms of y. That includes your bounds, and that includes your function, and then your thickness. All will be in terms of y. So the volume of the solid, we're adding up an infinite number of these disks that are stacked on top of each other, is going to be the integral from a to b of pi r squared times the thickness, which is dy. Okay, so do one example. Find the volume of the solid creating by rotating the area between the x-axis, y equals x squared plus 3, x equals -1, and x equals 1 around the y-axis. So let's draw what our function looks like. C3, and then that is going to be a parabola. Okay. Between -1 and +1. And the x-axis. So my area is going to be here. So I'm rotating that area, and it says around the x-axis. So it's going to look like this. And if you think about rotating, that means it's going to create some circular figures here. So it's like coming towards me, and then away from me, towards me, and then away from me. So I'm going to redraw it here on the side. My figure is going to kind of look like this. Oh my gosh. Clearly not an art major. Okay, something like that is kind of what it creates three-dimensionally. That's what it's going to look like. So again, I'm going to have my representative. It's kind of hard to make the colors pop. I'm going to have my representative rectangle here. If I take that rectangle and I rotate that around, that gives me a disk. The thickness of that disk is going to be dx. So the volume of my solid is equal to the integral from a to b, which I'll figure out here in a second, of pi r squared h. H is the thickness, which is going to be dx. That's important because that tells me that I need to have my entire equation written in terms of x. So the function itself, f of x, is what my radius is. Because no matter where I am, that radius is going to be touching the top of my function, x squared plus 3. So my function is my radius. Again, in terms of x, since I have a dx, the thickness of each disk is dx. And then the a and b values, we're going from -1 to 1, because that's where my bounds begin and end. And this does say find the volume, so I'm going to go ahead and solve this. Pi is just a constant, so just take it out. X squared plus 3 squared would be, using the FOIL method, x to the 4th plus 3x squared plus 3x squared is 6x squared, plus 3 times 3 is 9 dx. So antiderivative would be 1/5 x to the 5th plus 2x cubed plus 9x from -1 to 1. Hopefully I left myself enough room here. I'm going to plug in 1. I get 1/5 plus 2 plus 9. Plug in -1. I get -1/5 minus 2 minus 9. So if I combine like terms, 1/5 plus 1/5 is 2/5. 2 plus 2 is 4. 9 plus 9 is 18. So 4 plus 18 is 22. And you don't have to simplify. So 22 plus 2/5 pi. If this was multiple choice, however, you would need to simplify. So just remember how to add your numbers and fractions. 22 times 5 is 110. So that would be 112/5 pi. Technically, this is in units cubed because it is the volume of a solid. So you should have units there as well. But you know, that part's not new. You should know how to solve an integral. Just pay attention to whether the problem set says you're allowed to use a calculator or not. You should also know how to use your calculator to solve an integral. The big thing here is the setup. That's the only new part really for this problem. Pi r squared h is the thickness of the disk, and that r is the function.